Hello all, welcome to Shakti's AI Junction. In this video, we will talk about transformers in NLP. Why transformers? Our traditional NLP tasks such as machine translation, sentiment analysis are performed with recurrent neural networks. These transformers capture relationships and the dependencies between the words in a much more efficient way and effective way than our sequential models like RNNs. Google introduced the first transformer model in 2018, which is a BERT, bidirectional encoder representations from transformers. BERT has achieved remarkable results in various NLP tasks such as question answering, named entity recognition, and text classification. So how transformer learns? It learns to predict the missing words or next words in a sentence using a process called unsupervised pre-training. After pre-training, the model can be fine-tuned on specific downstream task with a smaller amount of labeled data. So this is architectural diagram of transformer model where it has encoder, decoder, multi-head attention unit followed by normalization unit, residual connection unit, feed-forward neural network, and again residual connection and layer normalization is added to feed-forward neural network. And similarly, the decoder also has, two sets of multi-head attention followed by a feed-forward neural network and the linear layer and the final softmax function. I mean, both encoders and decoders has a positional encodings, which we will discuss it step by step. So I have broken down the components into 8 parts. Input embeddings, encoder and decoder, self-attention layers, multi-head attention layer, feed-forward neural network, positional encoding, residual connection, layer normalization, and masking. So we will, I will give a high-level understanding of all these individual 8 components. And out of this, self-attention layer is the most important one. It is it forms the crux of transformer model where it does become a huge hit. We will have a follow-up video on the self-attention layers, but for now, I will give a overall understanding of what it is. Input embeddings. The input sentence or the sequence has to be converted into a numerical representation so that the machine can understand. These numerical representations are called as embeddings. So basically each word or element in the sequence is mapped to a high dimensional vector which captures the semantic information or contextual meaning. Okay, so these embeddings, for example, I love India. So each word or a token like is mapped to a vector and which is that what you see in the numbers 0.2, 0.4, 0.1. So these numbers will be given to our model because machines can understand only numbers, not the text. And the main idea behind this input embeddings is similar words will have a similar vector representations. For example, king, queen, and horse. So this king and queen words will have similar meaning as so like they have a similar vector representations in the vector space. So with this, the transformer model will be able to capture the relationships and the generalize better. Encoder and a decoder. The transformer consists of an encoder and a decoder, where the encoder processes the input sequence and the decoder generates the output sequence. Both the encoder and the decoder contains multiple layers of self-attention. Like this is that. The first one is that encoder and the second one is the decoder. Self-attention layers. So this is the main important part of our transformer model, which is a self-attention layer. In self-attention, each word gives attention to other words depending upon its relationship or relevance among the other words in the same sequence. Thus, it allows a model to capture the importance and the relationships between the elements. So we will have a follow-up video on self-attention layers with examples and we will deep dive into it. And I have shown you an example, I love India. So this I word will assign weightage to other words like love and India. Similarly, love will assign weightage to I and India, and India will assign weightage to I and love. So this is the process and it goes on. We will discuss in detail in the next video. Multi-head attention layer. So the self-attention is performed multiple times in parallel, which forms a multi-head attention layer. And the main, this is why are we doing this? It is to understand the different subspaces or different aspects of our information. For example, the cat sat on the mat. The self-attention layer one, it focus on the syntactic relationship by giving weights to the word cat and sat. The second self-attention layer, it focus on the semantic relationship by giving weights to the word cat and mat. The third self-attention layer gives focus on the contextual relationship by giving weights to the words the and on. So in order to capture the different aspects of the same sequence, we are, running or executing the self-attention layers parallelly, which is forms a multi-head attention layer. Okay, the next is a feed-forward neural network. The output of this self-attention is given to a feed-forward neural network. Feed-forward neural network is nothing but it has two linear layers with one non-linear activation function in between them. So here the output of each position in the sequence, is fed to feed for a neural network, and it's an element-wise operation, and it produces a new representation for each position in the sequence. Like the I love India, it has three positions. So this a feed for a neural network will provide a new representation for each position in the sequence. So this is to capture the nonlinear relationships better. uh, like it, as I said, it has two linear layers with the nonlinear activation function in between them. The first linear layer will map the, will project the information onto a higher dimensional and followed by a nonlinear activation function. And the second linear layer, it will map again, it will bring back to its original dimension after understanding all the linear relationships or the complex relationships within the sequence. So this enables or this understands the nonlinear relationships and the model complex interactions. Positional encoding. So the transformer should know about the position information of the token as the informations get a progress at each phase. So how can we do for positional encoding is by creating a vector of the same dimension as that of your input embedding by using sine and cosine functions. This positional, matrix is added element wise to the input or word embeddings for each position in the sequence. So it's like, imagine like you have an input embeddings of 5-dimensional, then you are again creating another vector dimension of, a vector matrix of the same 5-dimensional, and you're doing an element wise operation. So what the output will be like, you will have meaning of the token as well as the position of the token. So in this way, we will get both meaning of the token as well as position of the token, which is done by positional encoding. Residual connection. One of the more important, one of the problem in neural network is the vanishing gradient descent, which means our gradients becomes too small to update the weights during the back propagation. In order to avoid, we are having a residual connection, which means like we are skipping the intermediate layers. So imagine there are a lot of layers, and the weight, and when the gradient, passing through each and every layer, it is becoming so small, so which is not able to update the weight properly. So if we can get rid of the intermediate layers, then we can have the gradient to flow completely through the network. So we are just bypassing the gradient by directly, passing to the output layer. Okay, that is what a residual connection, which means we are skipping the intermediate layers. So in this way, when the gradient can flow through that entire network, it will be able to learn the long range dependencies to improve the overall performance. Layer normalization. So layer normalization, we're gonna normalize the each positions or the representations at each positions across the entire dimension. Like if your dimension is a 3-dimensional vector, and each position will be normalized. So this will be this will allow the model to stabilize and speed up the training process. Normalize in the sense like you're doing that on a, likewise you do in the feature scaling in our EDA. Similarly, we have to do normalization where the output will become between 0 to 1. And masking. Masking is nothing but adding special tokens called as a padding to your input sequence. Let's say your predetermined sequence length is 10 or something, and your input sequence length is 5. Okay, this 5 under 10 this length has to match, because in our transformer models we do a lot of element wise operations. So if the dimensions are not same, then these element wise matrix multiplications cannot happen. In order to have the consistency, we are adding padding. Padding is nothing but adding extra zeros to your input sequence. Okay, so the machine will, the transformer model will understand during the processing by ignoring the positions with the zero values, which means that is a that was added as a padding during the masking process. Thank you all. So this is a short understanding of transformers and its components. We will have another follow-up video on the self-attention layers. So thank you all. Please like and subscribe to Shakti's AI Junction. Thank you.